Okay, YouTube, in this video we're going to continue our exploration of the rational roots theorem to find possible rational roots for a polynomial, but basically just putting it to practice. So we have some function g of x here, y equals this, and what we want to do is find all of the real zeros of the function, or all the x-intercepts. So when we say x-intercept, remember that what we mean we're doing is we're setting y equal to 0. So the first thing we need to do before we solve this is we need to set y equal to 0, or at least gather all of our x terms on one side of an equation with 0 on the other. So that being said, we say, well, first of all, the thing we would do is we would try to factor this. Now, you may go ahead and try and factor this by grouping, say. It's got 4 terms, but you'll see that grouping fails. So essentially what we have to rely upon is division at this point. So we say, well, what could possibly go into this third degree polynomial function? So we say, let's make our list of possible rational roots. Recall that this is the set of factors of the constant term, or the set of factors of the leading coefficient. So we say the set of all of these is this quotient here. So we say the factors of 16 are 1, 2, 4 goes into 16, we say 4 times 4, and then 2 times 8, and then 1 times 16. And we say the factors of the leading coefficient here are 1 and 3. And this is all plus or minus because we can have either positive factors of a number or negative factors of a number. So when we write this out in roster notation, which is really what we should be doing, which means everything individually once you've gotten this primary list, then we get 1 over 1, which is 1, 2 over 1, which is 2. Of course, anything over 1 is going to leave itself, so we get it out to here. And then we also get 1 over 3 is a possible rational root. 2 over 3 is also a possible rational root. So is 4 over 3, 8 over 3, and 16 over 3. So are all of these. Oops, not 13, 8 over 3, 16 over 3. So this is the set of possible rational zeros. This is the possible. Okay, so out of all of these, what we normally do is we just start trying easy ones. First, like 1. We're going to try to divide out by 1. So I'm going to show you here. I've already made a graph of this, as a matter of fact, and it's kind of bad of me to say this, but I usually say go look at the graph first. You know, it's going to tell you some possible ones you should start guessing with. But I want you to see here what it looks like when you probably don't get some to work for you right away, not to give up. So when we bring in this 1 right here, we say maybe 1 works. We say the leading coefficient gets carried down, and then we'll start up. We say, okay, so negative 3 times 1 is negative 3, plus this is 17. 17 times 1 is 17, and we get the difference between these two things, I think, is a negative 19. You could see really easily right now that this isn't going to cancel out with our 16 and leave a 0 here. So it's not worth your time to continue to pursue it. The thing we would do next is we will say abandon positive 1, but we try maybe negative 1 as a possible 0. So we say, is x equals negative 1 a possible, is it a 0? We say, well, let's multiply. Negative 1 times a negative 3 is a 3. Plus 20 is 23 times negative 1 is negative 23. So this gets more negative, like it's negative 59, and that's totally not going to cancel with the 16. So what we're saying here is essentially, negative 1 here, it's not going to happen. So maybe we cross this off the list and we say maybe 2 would work, just maybe. So we say 2 times negative 3 is a negative 6, plus our 20 here is a 14 times 2 is 28. And the difference between these two values here is 28 plus another 36, or actually not a difference, it's a sum. So adding these two up here, we get a negative 8, and then 2 times negative 8 is a negative 16, and then we get a 0 here. So it looks like we stumbled across a 0. I made a graph of this, as I mentioned before, and you notice here that 2 is indeed one of our zeros. Now, the things we want to point out here are these. We say, well, first of all, whenever you come across a 0, man, write this thing down. We could say solutions, or zeros, or x-intercepts, or roots. We say x equals 2 is one of them. Now, I know I have a third degree polynomial, so I suspect there are 2 more, but the thing we need to recognize is now we have negative 3x squared plus 14x minus 8. Is what the leftover polynomial is. So what this means is really the original polynomial could say if, well, x equals positive 2 was a 0, then x minus 2, this was, recall, a factor, but we get a positive 2 producing this factor here, x minus 2, times this leftover negative 3x squared plus 14 x minus 8. You multiply those back out, you get your original, we'll say, g of x back. So if this is the factored form where we're saying, well, it's all, it's all here set equal to 0, then we could set each of these equal to 0 individually and solve. But the thing here is, the question I have is, at least, is this factorable? And I suspect that it is because I do have the graph here and I see that I get 4, and, it looks like 2/3 here to foreshadow a little bit. But if we did factor this, look, we have a trinomial where a is not 1. So the first thing we would do is multiply the constant and leading coefficient terms. We get 24 here positive. And I want to know, can we think of two numbers that multiply to be a positive 24 that add up to be this 14 right here? We of course have 2 and 12. So what we could do is we could factor this polynomial, at least I'll do it off on the side here, plus 14x minus 8. We could rewrite this polynomial, splitting up the middle term here, negative 3x squared into a 2x and a 12x. And those are the same two things that produce this negative 14 here when you sum them. But we'll solve this by grouping, okay? So we say, all right, group these terms, factor out their greatest common factors. We say x squared, we leave behind a negative, actually let's do a negative x squared, let's do that, which is different, I understand. We say negative x squared would give us a positive 3x here minus 2. And then we say over here, factor out a 4. And we get a 3x minus 2 as well. So these two factors now match, and we can factor them out front, and we get, so 3x minus 2 is another factor, and we get x squared plus 4. And there's a negative x squared plus 4. And the thing I want to comment on here is it would be most appropriate to factor out a negative 1 out front of this. And what that's going to do is, and I'll even write it this way, I suppose. I'll write it out in front of this, just so you don't get too uncomfortable with it. But we're going to factor this negative 1 out of both of these terms out in front of it. And we get this, we get x squared minus 4, which is also interesting here, or x minus 4. Sorry, this is an x to the first power. So, okay, so this is better. We say we get x minus 4 instead with the negative 1 coming out front. So, stashing this here, we get x minus 2. And we factored this into positive 3x minus 2. And we were able to factor this into x minus 4 and then a negative 1 here. And this all equals 0. So now the thing we can say about this is if this times this times this equals 0, then we can set each of these factors individually equal to 0 and solve them. Now, one thing I do want to comment on before we solve for x in each of these equations is this negative 1 that's sitting right here. We could actually right now, since it's set equal to 0, divide both sides by negative 1, and that's going to cancel this out, and we just get 0 on the right still. So basically, 0. We can neglect any factored out constants, okay, or scalars we call them. So we say here we get x equals 2, but this is one we already discovered right here. The other two we're going to discover are when we add 2 and divide by 3, we get x equals 2/3, positive 2/3, which mind you was on our list of possible rational roots. So we say 2/3 is another 0, and then we say here x equals 4, which was also on our list right there. And we say, okay, so just by finding one from this potential list here, we were able to go find the rest. And also, we can always go look at the graph.